Hello everyone, welcome to lesson 4-4, scientific notation, found on page 153. Now, we have different ways of writing numbers. One way, the typical way, is standard notation, but this one is scientific notation, and it's for writing large numbers. For example, let's see, this lesson we're going to learn about express numbers in standard form, which is the normal way of writing it as a rational number, and in scientific notation. Compare and order numbers written in scientific notation. Okay, so we're going to compare them and write them in scientific notation. And this is what we use scientific notation for. For very large numbers, such as when we talk about numbers in space. Earth is the third planet from the Sun in our solar system. Because Earth's rotation about the Sun is not circular, so it's oval, the maximum distance between Earth and the Sun is about 95 million miles, and the minimum distance is about 91 million miles. So when we're writing 95 million and 91 million, that's a large number. That's a lot of zeros to write. So in order to save some space and not have to write so many zeros, we use scientific notation. Let's look at the key concept. Scientific notation. A number is expressed in scientific notation when it is written as the product of a factor and a power of 10. Okay? That means we're going to have a power of 10 with the exponent times the number. You'll see what I mean in a minute. The factor must be greater or equal to 1 and less than 10. For example, here is the number written in scientific notation. We have 3,500,000. Okay, 3,500,000. We want to leave one whole number, so we're going to write it as 3.5. And then we count 1, 2, 3, 4, 5, 6. All these 6 places will become 10 to the power of 6. Do you see that? So it becomes 3.5 times 10 to the power of 6. I could have zoomed that in, sorry. And then when it's a decimal, you already know that a negative exponent makes it a decimal. It makes it a fraction, a number over. So it would really be 4 times 10 to the power of 5, right? Which would be 5 number places, 1, 2, 3, 4, 5, right? But because it's negative, it's 5 towards the decimal side. Okay, make note of this. It's very important. So here's what I was saying about scientific and standard numbers. Numbers that do not contain exponents are written in standard form, regular rational numbers, right? However, when you deal with very large numbers like 12,760,000 or very small numbers like, let me see, 0.000001276, it can be difficult to keep track of the place value. A number that is expressed as a product of a factor and a power of 10 is written in scientific notation. When a number is expressed in scientific notation, the exponent tells you how many places to move the decimal point. Okay? Let's look at the example here. Here we have 2 times 10 to the power of 3. Well, we write the 2, and then we have to the power of 3, 1, 2, 3. Simple, right? We keep the whole number, 6.8, right? Times 10 to the power of 5, so 5 places. So the decimal place is going to move 1, 2, 3, 4, 5. Okay? And here, again, a whole number. Oh, but now we're going the negative. We have a negative exponent, so now we have to move in the negative direction. 1, 2, 3, 4. You'll see. See? 1, 2, 3, 4. There it is. Okay? Because it's a negative, it becomes a decimal. Okay, let's try these 3. Now would be a good time to pause the video and try it on your own, and then play the video to see if you got them correct. Okay, so go ahead and pause now. Okay, so we have 4. Remember, this is like saying, right here, this number is like saying 100. 10 times 10 is 100, right? So it's 4 times 100, so it's 400. Okay, or as we said, you keep the number, and the exponent tells you how many places you need to move the decimal. So you moved it twice. 1, 1, 2, right? Okay, 1b is, you have to move it now 7 times. So I have 5. I'm not going to write the decimal because I'm going to move it anyways. 1, 2, 3, 4, 5, 6, 7. What is that? That is thousands, 100,000. That's 59,400,000. Okay, and now we have it, we're moving in the negative direction. So I have, I'll write it this time 1.3, so you can see how I'm going to move. And I'm going to move 3 times to the left. 1, 2, 3. So my answer becomes 0.0013. For example 2, now we're going to go the other way. We're going to go backwards. Now we have the standard notation, and we're going to write it in scientific notation. That's simple. Remember, keep one whole number, right? And then count the number of zeros, 1, 2, 3, 4, 5, 6, and you make it a base 10 to the power of 6. So this is expressing the number of zeros. The exponent is expressing the number of zeros. And here, same thing. So you have 0.02. So you want to make sure that you can move it 2 places right there, so that you have one whole number. So that becomes 7.2. All right. But then to be able to go this way, remember you have to multiply by a negative exponent. So 10 times 2, because it moved 2 times, right? To make it 7.2, you have to go 1, 2, and to go from this to this, you have to go 1, 2, the other way. So it's 7.2 times 10 to the power of 2, negative 2. Okay? Okay, so go ahead and try 2A, 2B, 2C. Pause the video now and then check to see that you did it correctly. Pause now. So 2A, we have 9 times 10 to the power of 2, right? Here we have 1.89, and how many numbers? 1, 2, 3, 4 times 10 to the power of 4. And C, in order for me to take this decimal and make this the first a whole number right here, right, 6.4, I have to jump 1, 2, 3, 4, 5. Okay, so it's 5 of them. So I'm going to write 6.4 times 10 to the negative 5. Make sense? We use scientific numbers to estimate as well. For example, one way to estimate a very large or a very small number is to express it in the form of a single digit times an integer to the power of 10. For example, the population of the United States in 2010 was 308,745,338. Now, if we wanted to round this, boys and girls, to the nearest million, we would make it 300 million, 100 million, right? We would get rid of this 8 million right there. So we could just make all those zeros, and we would write it as 3 times 10 to the power of 8. You see? 1, 2, 3, 4, 5, 6, 7, 8. And it stops at the 3, makes the 3 a whole number. So 3 times 10 to the power of 8 is an estimate of that number. Okay, you can try it here. The population of Kansas is 2,853,118 people. Write an estimation in scientific notation for the population. Well, this could be rounded up right to 3 million, right? It's almost 3 million. We're only missing it by about 147,000, right? So we round it up to 3 million, and there it is, 3 million, and it's 3 times 10 to the 6th power. 1, 2, 3, 4, 5, 6. There you go. Okay, let's try it with these 3. Pause the video now and try it, please. Okay, for the first one, I would round 3,600,000. I would round that to 4 million, right? So now I have my 4 times 10 to the power of what? Times 10 to the power of 1, 2, 3, 4, 5, 6. There it is. Okay, here, how far did I move to go to make this a whole number? 1, 2, 3, 4, 5, 6, 7. So it's 10 to the power of negative 7. Got it? And they want us to estimate, so that's a tough estimate to make. Should I round that up to 3, or maybe I'll just do 2.5 times 10 to the power of 7, or if you rounded it up to 3 times 10 to the power of 7, you are not wrong. Okay? And this one can seem a little tricky, okay, because we have 1, 2, 3, okay, 3 places. That makes it a negative 3. But really, boys and girls, this is such a small value, okay, 215 thousandths, such a small value, and it's less than 0.5, so we can just get rid of it. And we can write it as 4 times 10 to the negative 3rd power. And there you go. Example 4. The space shuttle traveled about 8 kilometers per second. At this rate, that's actually really fast, 8 kilometers per second. Wow. In 1 second, it can go 8 kilometers. That's amazing. That's, understand that's much more than the charity road race in 1 second. At this rate, the shuttle will take about 4.5 times 10 to the power of 4 seconds to fly to the moon. Is it more appropriate for a newspaper, who's reporting it to the general public, to report this time as about 4.5 times 10 to the power of 4 seconds or about 12.5 hours? Explain your reasoning. Well, boys and girls, you should know that people are more familiar with time written this way than written this way in seconds, right? The measure of 12.5 hours is more appropriate. The number of 4.5 times 10 to the power of 4 seconds is very large, so choosing the larger unit of measure is more meaningful. Yeah, we don't live by seconds. We don't say our class today will be 3,600 seconds. No, we say it'll be 1 hour, right? So we live simply by hour or even minutes if it's a shorter amount of time. So yeah, it would be more appropriate. Let's look at number 4. A dime is about 5.875 times 10 to the power of -3 foot in diameter. Okay. Again, why are we measuring a dime, which is a tiny coin, a very small coin, in feet? Why are we doing that? A foot is too large of a measurement. Is it more appropriate to report that diameter of a dime is 5.875 times 10 to the -3rd power foot, or is it 7.05 times 10 to the -1 inch? Explain your reasoning. Well, boys and girls, inches will make more sense, right? Because it's a smaller form of measurement. So therefore, let me write, therefore, 7.05 times 10 to the power of -1 inches would be more appropriate because a dime's diameter is not very large. Choosing a smaller unit of measure is more meaningful. Please write this down and circle it like that after you write it down as a key answer. You can do it on the margin of your textbook. On the margin meaning on the side or just under the question. I don't think you'll have enough room here to write it. So you can write it on the side and circle it. Another key concept is comparing and ordering the numbers. To compare and order numbers in scientific notation, first compare the exponents, right? The bigger exponent is the bigger value. With positive numbers, the number with the greater exponent is greater. If the exponents are the same, then that's when you compare the base, you compare the factors. So look at the example on the right with the geologic time periods, okay? So times when dinosaurs existed and different species on Earth existed. So we have the Jurassic, the Silurian, the Tertiary, and the Triassic. Okay, and you can see that we have to the power of 8, power of 7, and power of 8. So the Tertiary is the youngest, and the oldest will be among these three, and the one with the highest factor. So the Silurian is the oldest, and you can see that, and they explain it right here. So you can take a look at this, take your time to look at it. But right now I'm just going to work ahead to look at number 5 for the sake of not making the video so long. And for number 5, approximately 1.372 times 10 to the power of 7 square kilometers of Antarctica and about 1.834 times 10 to the power of 6 square kilometers of Greenland are covered by an ice cap. Which landmass has a greater area covered by ice? Well, guys, this one's only to the power of 7, while this one's to the power of 7, while this one's only to the power of 6. So clearly, this one's going to be bigger because it has one additional place value. Okay, so Antarctica has more area covered by ice. Okay, copy that down and leave the guided practice and the independent practice for class. Okay, so just do the video. See you in class, everyone.